You see a page from the book, and in my book it is page 225. It can be in another edition, maybe 223 or so, but it's about the differential pair, and it was the test circuit for the differential pair, nothing else. It's not the application of a thing, it was just a circuit to show you how the transfer of a differential pair is an odd function and the common mode is an even function, so the common mode voltage. And that was basically only to generate these plots. And I was a little bit surprised when people started to make the controller with a differential pair that I found a voltage controlled voltage source with a gain of -1 connected to one of the inputs of the differential pair. So obviously it wasn't clear to you that this was just a test circuit to test this differential pair, and it has nothing to do with every application of it. So the procedure for making a controller is very, I hope I can make it very clear. For me, it is very clear. Let me hope to make it very, let me help to make it very clear for you as well. So we wanted to make an amplifier with an integrating transimpedance amplifier, brute force 50 ohm, and a load. And the source was a voltage source, a capacitive voltage source. So this is the antenna, this is the amplifier, and this is the load. We want to have negative feedback, which means that if we put plus here, that it should be minus here because there should be one inversion in the loop. So plus, minus. And now we are thinking about a controller. Well, you see, a single stage controller is possible because with a single CS stage, we could do this to the gate, this to a drain, and this to the source. But now your design task was to design an amplifier in which the first stage was a differential pair. I didn't do that. I used a single CS stage, a current mirror for extra inversion, and then again a CS stage, but now complementary parallel. The question for you is to replace the combination of this single CS stage and the current mirror with a differential pair. So what we are going to do is we are going to design a controller and place it in this box. That is what we do. Forget about all the biasing. Why? Because biasing we do later. It is useless to bias an amplifier that's not good enough. So we don't spend energy on biasing as long as we don't know that the amplifier is feasible, stable, and we cannot then measure the distortion because for that we need biasing. So at the moment that we really need the biasing to evaluate the distortion, we will be sure that the bandwidth is okay, the stability is okay, and then we are going to add the biasing. And this we will do Thursday. But now our controller. Let's draw the controller, and the controller looks like this. We have a differential pair at the input. So forget about biasing, and I don't care about P or N at this point. I just want to see the structure. And we have the input of the second stage of the controller, which is a CS stage, connected to the output of the first stage. So you can also do plus and minus signs in here. So as soon as you cross a gate drain, you have one inversion. So here's one inversion and here's another inversion. So that makes this minus and this minus. Now we have two options. So this is just straightforward design. We don't start with circuits that we know or that you have seen before or whatever. No, we want to make you a designer that can invent without knowing all solutions that have been invented by other people. Of course, It is nice to know them and good to know them, but we want you to be a designer that can, in situations that there is no solution, generate a solution by using methods and techniques. So plus minus means I can put this one here, but then the source must be put there. Another option is I can put this minus one here, then it will be minus plus minus, and then the drain will be there. In the last case, the source of this one, of the complementary parallel, will be connected to the signal ground. So this will then be connected to signal ground, and this will be connected to signal ground, and here will be the feedback capacitance. In the first case, the source will be connected to the load, and the drain will be connected to the ground. This is a nice one. Well, nice one. I don't know if it's nice, but let's say it's an option. So we can just flip the whole thing and place it in there. And there are two options. And if you would make a computer to design this, and that's what basically what we want to make a design theory so that you can automate parts of the design, then you must have an argument to select one or the other. And at this point, I don't have. I don't know yet if it is better to place it like this, because one I must invert, or to place it like this. I don't know. So we can do both. And then we can study, for example, the biasing and see which one is easier to bias. And then we can say, oh, there one is easier to bias, so we select that one. Then we have an argument of doing so. But at this point, at this moment, I don't know. I have no argument. So I can do both. So let's do a strange thing. Let's start with, so we again draw the box. I have my feedback capacitance and the load, blah, blah, blah. That is all the same. And the source, it's also interesting. It's of course how to place the controller in it. And now I want to place the controller in it like this. I want to do it in a way that it is not really looking very handy, but just to play with it and to show you that you must really forget about existing solutions and just be able of generating something yourself. This was the second stage, and I decided to put the source on there. So I have here, let's call this plus, and this must be minus. This is minus, so it should be at a output of the differential pair, which is the plus one. Well, just put the differential pair in it, just don't connect it yet. So we have a differential pair here. Oh, this is the sources. If I call this minus, then this will be plus, and this will be minus, and this will be plus, so I must connect it like this. That's nice. So you see, this is one solution. Connect it like this. And if I would draw it later for biasing, maybe you want to draw it in a more convenient way. Maybe you see, okay, so so then maybe you want to draw the and that's what we are going to do Thursday. Maybe you want to draw your differential pair like this, if it is an N type, and you want to say, well, okay, then what I need, I have here my output stage, and if this is the input for my source, if this is the input, then so this is the minus, then I need the output stage. It will be connected. Looks this the gate of the output stage will be connected to the one that is connected to ground. So this is connected to ground. So this is the gate. And the source will be connected to the one that is connected to the plus. So the source is here connected to the plus. And this will be the output. And this one is ground. And this will be the output. So here's your feedback. And now you think, well, let's if you draw this upside down, maybe you think this has become a common drain. but it's not common drain. It's still common source. Look, this is the input port and this is the output port, and they share the source and not the drain. But if you decide to do this for bias reasons, you suddenly change the stage to common drain, because now this is the input. I mean, sorry, you connect this, yeah, this one, yeah, yeah, you connect this one to ground, see? So this is one option. The other option is, of course, having, well, let's put it in the other direction immediately, having my source connected to ground and my drain to the output. And then so this is source, this is source, this is source. Then if this will be the input for my signal and this will be ground, so this is the input for signal, which makes it the capacitor and the signal source, then I must, and this is also ground, then I must have a non-inverting here. So this will be connected to ground and this will be connected to this stage and this will be the output. It's very formal. The only thing you do is you connect the output of one stage to the input of the next stage, and you realize yourself, what kind of degrees of freedom do I have to place the whole thing in it? And you don't, why should I add this inverting voltage source that was just a test circuit for my differential pair? So I saw here people placing the -1 gain controlled voltage source. We are building an amplifier. So this was the amplifier. This was a structure. And of course, we don't use now the balanced pair completely balanced. Look at the solution here. Two terminals are connected to ground. So my balanced pair has one here to ground. So, and the other one there to ground. Yeah, what is not so balanced at all. That has some influence on the noise performance, and it is discussed in the book. But okay, for the moment, let's not focus too much on that. But the procedure is, first we design the concept of the amplifier. Then we have a two-stage controller. Then we place the controller in the box. And that's it, nothing else. And in the controller, output stage or sequential stages are connected to the output of the preceding stages. That is the procedure, nothing else.